And I said, believe it or not, that this definition actually, there are immensely many equivalent definitions. Since someone told you, at least, we were not here last time, what do you think? What is a tangent vector to a manifold? Do you know, Henry?
One of them is derivation.
Ah, you know, well, yes, you're told to Bragg to ask you. And you?
Yeah,
you know what tangent vector?
In local coordinates.
Some. You know, any definition which involves local coordinates, it is a definition of the theorem. It's dangerous because you need to check that this doesn't depend on this, that doesn't depend on that, and so on. It is, more convenient to have an invariant definition. And this is precisely what I did last time and what I want to repeat now, and we will discuss the properties of tangent vectors. So, X is a manifold. And then there arises a ring. So X is a manifold. There is a ring of functions. C infinity of X, all real valued C infinity functions on X. Then we also need to have a point P in X, and the tangent vector to X at P, Xi, is a linear map I write R, I consider real manifolds. Is a linear map, linear in the usual sense, such that the following product rule holds C of F times G is equal to C of F times G of P plus F P times C of G. The usual product rule. From the point of view of sort of usual geometry, this means that speaking of tangent vectors, we mean mostly the derivative of functions with respect to this vector. And it is very convenient just to define tangent vectors as such linear maps with this property. It is not precisely derivation, because the values are not in C infinity X. Derivations, Henry, as you probably know only well, are vector fields. It's just one vector. So values are numbers, and P is fixed. Now, Txp, T sub Px is the space of all tangent vectors. Tangent vectors to X at P. It is very clear that this is a vector space. If you take the sum of two tangent vectors, the usual sum of two maps of two operations, it will be a tangent vector. If you multiply a tangent vector by a number, it also will be a tangent vector. So this is a real vector space. And at the first glance, it seems immense, very big, because C infinity of X is a huge ring. But still, in reality, this vector space has the same dimension as the manifold. We will see it. I want to begin with some very obvious property. Well, obvious or not, you can judge yourself. Some properties of all tangent vectors. First, there are constant functions, right? So let C be a constant. Then Xi of C is 0 for every tangent vector C. Property 1. Proof is very simple. Since Xi is linear, it's sufficient to prove that Xi of 1 is 0, right? And 1, whether you agree or not, is 1 times 1. By this reason, Xi of 1 is equal to Xi of 1 times 1. And according to that rule, well, 1 of p and 1 is 1, certainly. So this is just 1 times Xi of 1 plus Xi of 1 times 1, which is 2 Xi of 1, which definitely Xi of 1 is equal to 2 Xi of 1, which definitely implies that Xi of 1 is 0. This is one property which I wanted to mention. Another property has, well, very slightly longer proof, but still is expectable. It's locality. Suppose that our function f is 0 in some neighborhood of p. So property is formulated in the following way. Let f be 0 in some neighborhood u of p. Then again, Xi f is always 0 for every tangent vector. It's a very important thing, actually. Why so? Let me draw a very funny picture, but certainly my proof will not logically depend on it. So this is f. This is p. Now I consider another function, which is actually 0, excuse me, 1. So this is f, this is g. 1 in the complement to some smaller neighborhood than u. And still it is 0 in some neighborhood of p. Actually at p is all I need. So g of p is 0 and g of x minus u is 1. Then, you know, also it's an infinity function. Then you know, if you multiply f by g, you will get f. Because where f is not 0, g is 1. Right? After which I have nothing to do. It's Xi of f. This Xi of f times g is Xi of f g of p plus f of p Xi of g. In both, the things are 0. So this is 0. This second property actually is very important. No, the first is also important. But the second is very important because it shows that actually if two functions agree at some neighborhood of p, then the value of Xi of these functions are the same. The difference is 0 in the neighborhood of p, right? Now, this small property gives us possibility to apply Xi to functions given not globally, but only in some neighborhood of p. Imagine that f actually is defined only in some neighborhood. So u is a neighborhood of p. Then, well, we proved it. We discussed this. It's possible to extend f to a function on the whole x but not from U, from some smaller neighborhood. Then there exists a function g, x, in R, such that g and f agree on some neighborhood of P, which is contained with its closure in U. We did this. And this is very simple. Follows actually from what? After all, as everything follows from, we need to apply the partition of unity to prove this. But otherwise, it's very simple. Then what to do? How to define C of f, where f is defined only in some neighborhood of P. We apply it to G. By definition, C of f is X of G is defined. A natural question arises with a natural answer. This visibly depends on G. Certainly there are different ways to extend the function f to x. But for every two extensions, so if f of maybe of w, where w is also a smaller neighborhood of P, is equal to h of w, then G and h agree on some neighborhood of P, and by this reason we have just proved X of G is equal to X of H. So this is well defined, and this really gives us an opportunity which we will use constantly. If we have a tangent vector, we can apply it to functions given locally. It's at a neighborhood of P. Agree? Questions? Well, so far it is all I need. And now I will, so imagine that you are very nice place at a lesson at elementary calculus. Because I want to prove a theorem belonging to elementary calculus. If you teach calculus, you can use this fact for your midterms. Why not? The lemma which I'm going to prove, with all its triviality, actually is used in how to say, global differential calculus, differential topology, everywhere. So I prove it now, we'll use it now, but we should remember it, because we will use it also in the Morse theory, well, in many places. So lemma, absolutely elementary lemma. Forget manifolds, all this stuff. Suppose that we have a function of n variables. F x1 xn, and this, suppose that this is a function defined in some neighborhood of 0. Some neighborhood of the origin. Suppose also, so this is infinity function. I never mentioned, but I do not consider other functions. Suppose that f of 0 is 0 function, just take 0 value at one point. Then I want to say that, so claim, there exist functions f1, fn, maybe some smaller neighborhood of 0. I do not care about this. Again, of n variables, such that f They are not equal to 0 anywhere. But f such that f is equal to x1 f1 plus 1 plus xn fn. Is the statement clear? Is it believable? Certainly yes, if function f is equal to this, it is 0 is 0. Who can have any doubts? We need to prove the opposite to this. And I will do it now. The proof is not very interesting. It is usual trick which comes from lessons of calculus. So nothing unexpected. But still, since we now do not remember what a manifold is, still we remember derivatives and integrals. Otherwise, if you don't remember anything, I cannot help you. Just a second. Proof. I define fi as the integral 0 to 1. Let me denote this by x. D f is my function over dxi dx. The x is fixed here. T is not fixed. T from 0 to 1. You understand that the point x should be such that the whole interval, straight interval that joins x with the origin belongs to our neighborhood. So maybe we will have to take a smaller neighborhood. I claim that these functions satisfy these conditions. This is one claim. Another claim that it is immediately obvious. So I write the sum xi fi, sum xi okay, this of x. This is integral with respect to dt. This doesn't depend on t. So this is the sum. This is, integral to 1 of the sum xi now this, according to the chain rule, which you appreciate, is equal to the derivative of f of xt. Please don't say to me that it isn't so. Then your dt. Then your favorite fundamental theory of calculus says that it is f of xt, and this is f of x. F of x minus f of 0, f of x. So this is done. What is the level of difficulty of this theorem, of this lemma? Very important lemma. If you were algebraists, I would have said that in the ring of functions, the ideal consisting of functions which are 0 and 0 is generated by the coordinate functions, x1, xn. But since we are not algebraists, I am not saying that. Yes, this small lemma now is we need it for one reason. Well, certainly I need to formulate it, to reformulate it in, well, more general form. You will see that the generality here is again costs nothing. Now I consider a function which is defined in a neighborhood of some point p, not necessarily 0, and which is not 0 anywhere. So let f be a function u in the R, P1, Pn is in u, and no other assumptions. Then I claim that there exist functions f1, fn. Again, I don't write it, but I mean that given maybe in some smaller neighborhood of P, such that f of x, x1, xn, right, x1, xn, is equal to f of P times, no, plus x1 minus P1 f1 of x So this is the same lemma actually. Simply in this form I will apply it. And by this small reason I want to write this expression explicitly. It's clear that if we subtract f of P1, Pn from f of x1, xn, then the function will be 0 at P. And it's clear that if we make small coordinate change, namely denote xi minus pi as new coordinate, then it will be precisely our previous lemma. So no problems with that. Yes. Now it is time to prove something more essential. And something more essential is what I already formulated. That actually, which may seem surprising, the space of Tp of x has the same dimension as the manifold. So it is not too big and not too small. Moreover, I will provide a basis in this space. So so my claim theorem, but actually will prove more, is that the dimension, if the dimension of x is n, then the dimension of Tpx is also n. X is a manifold, Tpx is a vector space, both have dimensions, and there's a thing. I say that I will do more because I will provide a basis in this space. And then we just will count the number of vectors in this basis. I take a point P. And I take some local coordinates around this point. You remember, I introduced this language. So we have a chart which covers, we take a chart which covers P, and this chart brings, in some neighborhood of P, a system of coordinates, x1, xn, from the Euclidean space. Let's say P has some coordinates also. So in this local coordinate system, P, Pn. Now, I want to define n tangent vector. In Tpx. These are your favorite partial derivatives. So if f belongs to C infinity x, then in the neighborhood of P, f is a function of n variables xn, xn, x1, xn, and I write surprisingly di f is equal to the value of this partial derivative at the point P. All okay. The famous properties of partial derivatives show that this is tangent vector. It satisfies certainly linear and satisfies the product rule as it is well known. two things about these partial derivatives. The first thing is that they are linearly independent. And the second thing is that they span the whole tangent space. As soon as we do this, we have this result and more, because we have some basis. The basis depends on the local coordinates. So first, the i's are linearly independent. You remember tangent vectors, and the I in particular, can be applied to locally given functions. Locally, we have locally given functions, my local coordinates. Local coordinates are functions, which are given, which are defined where they are defined. Right? So we can apply di to local coordinates. I write di of xj is delta aj. Okay? Well, now, from this it certainly follows that the i's are linearly independent. Look, if the sum ai di is 0, and some a, say aj, is not 0, then I get a contradiction if I apply this to xj. Because this is certainly aj. The I of xj is normally 0, but only the j xj is 1. So yes. And this connects to this, because this is 0. So we have that aj is both 0 and non-zero, and this shows that these functions are linearly independent. Now we need to prove the second statement, namely that every tangent vector is a linear combination with numerical coefficients of the i's. So part 2. Part 2. Let C be in TPX. Then I claim that C is equal to the sum AI di for some real numbers. Any idea how to prove it? To prove such statement, your mathematical experience should be sufficient for that. We need first to find these AIs. And then we will prove the equality. So what is AI? How to define AI?
Apply the
Xi?
thing to x sub I.
Perfect. We have Xi. And as we all agree, it is possible to apply Xi to locally given functions, in particular to xi. So AI is here. And then we want to prove that Xi is equal to the sum with these AIs. Well, to prove that two tangent vectors are the same, we need to prove that whichever function we take, the values of this of the left-hand side and right-hand side of this equality on this function will be the same, right? So we have to take an arbitrary function. What to do next? You see, if we know a lot, if you read multi-hundred pages books in differential topology, we have many different tricks. We have choices and we don't know what to do. But we are more lucky because we have only one thing which we can apply. This is our lemma. So f is equal to the sum, well, first of all, f of p. You remember, C is the vector HP plus right? Let us compute C of f. First, we need to apply this to a constant, but we already know that this is 0, right? Constant, as in tangent vector, is 0. Now we apply it to this sum. Sum of products. So we need to use the product rule. It will be C xi minus pi fi of p. This we sort of don't know much about this. Plus the sum. Now we need to compute this at p. But if xi is equal to pi, then xi minus pi is 0, believe me. 0 times c of fi. The second last sum doesn't look too impressive. It is 0. What about this? What about this? This is certainly C of xi is ai. This was our definition. C of pi is 0 because pi is also a constant, right? So this is, the whole thing is the sum ai times FIP. This was the computation number 1. Now I want to compute di f using the same expression for f. All the same, instead of c, I have to write di, right? So this is 0. What do you think is partial derivative di of, maybe it is better to write dj because there's no dj here. If I apply dj to xi minus pi, I will get 0 if I is not j. I will get 1 if I is j, right? So the whole sum is not a sum anymore. It is just 1 times fi of p. And then 0 is 0. So I see that fj here, excuse me, dj of f is this, which certainly implies, if we compare these two expressions, that yes, c is the sum. Questions? Remarks? Very direct proof. Still, we had to apply some trick from calculus, this lemma. If it looks as a trick, if you do not consider it from algebraic point of view, where it is sort of seems obvious that the idea of function 0 at some point should have these generators. Well, thus Tn Tp of x, the tangent space, has dimension n. One thing, I now want to say something to you. Your suggestion of a definition of a tangent vector now becomes sort of viable. Look, as soon as we have a local coordinate system, then a tangent vector has coordinates. So we can say that tangent vector to x at p assigns to any local coordinate system at a neighborhood of the point P some n tuple of numbers, n real numbers, which you can call coordinates of this vector. The only thing which actually need to be added to this, which actually makes this property not very convenient if you take it for definition, is what happens if you take another coordinate system. How these two linear coordinates in Tpx are related if you consider two different local coordinate systems. But it's very simple. Suppose that we have local coordinates x1, xn, and local coordinates x1 prime, xn prime. Xi is a tangent vector at a point within the domain of both local coordinate systems. Then Xi is AI di. So I denote di d prime I, the derivative with respect to this coordinate system, where AI is Xi of xi. Very interesting. But also, this is B, let me write J, d prime J, where Bj is C of xj prime, right? How are these numbers A and B are related to each other? Nothing can be easier. To find B, we need to compute Xi, this Xi, on xj prime. So Bj is equal to Xi of xj prime is equal to sum of AI di, let me write this, dxj prime over dxi. Here we clearly see the matrix of transition from the basis di to the basis dj prime. And this matrix is well known to you. It is also called the Jacobian matrix of transition from one coordinate system to another coordinate system. So here, this gives, it is written in books. So I respect it. Here we come to the definition which you suggested. A tangent vector to a manifold at some point is a function which assigns to every local coordinate system in a neighborhood of P this array of n numbers, a1, an, such that if we take another coordinate system, then the transition from the numbers a to the rising number b is performed by the Jacobian matrix. This definition can be found in books. It is, certainly I didn't measure, I think approximately 10 times longer than my definition and much less convenient. But as a theorem, it is important. Now I want also to relate very slightly all this to geometry. Because whatever I say, whatever anybody says, everybody knows that a vector is an arrow. And whoever says anything different certainly just try to deceive you. I never deceive my students. No secret from friends. It is one of my principles. It's correct. If you take for x just Rn or open set in Rn. Now, what is a tangent vector? This is really the sum. Now we have coordinates defined once and forever in Rn, in open sets in Rn. We have coordinates. And certainly it is true that a tangent vector, there are tangent vectors di, derivative, first order partial derivatives, and their linear combination. They certainly should be depicted as arrows. So as soon as we have some fixed coordinate system, we certainly can define a vector as it is usually defined in high school intermediate algebra, or whatever, however it's called. Just vector is an arrow. Has the starting, beginning, and then you can say many other things. But the fact is that we have tangent vectors to Rn. They are simply vectors in Rn. Yes. Now I want to say a very small additional thing about tangent vectors. What if we have some manifold? And we consider all tangent vectors to this manifold. Absolutely all. Such a big set. But the set is also a manifold. Has a very natural manifold structure. Look. First of all, this Tx consists of the spaces, which are disjoint. Every vector knows the point at which it is applied. So we have a projection, which take this into P. Now I want to define a chart in Tx. This is the following. Take a chart in X. U is an open set in Rn, by definition. Take U times Rn. It will be also an open set in R2, you agree? Now I define capital Phi, U times Rn into Tx in the following way. Phi applied to what? To a point in U? Let me denote it somehow. Say A in U. And point in Rn. B1, Bn. And this is an element in Tx, but actually this is an element in T, phi of A, x. And in this space we immediately have local coordinates, namely coordinates coming from U. This is B1, B1 plus Bn, Dn. So a tangent vector is defined. As soon as we have a local coordinate system in X, a tangent vector is defined by a point in the domain in this local coordinate system, in the chart, and numbers. And in this, we apply it to the point, small phi of A, and at this point it is the linear combination as every tangent vector of d1 dn with the given coefficients. This is a map of U times Rn in Tx, and everything is very clear. It is is 1-to-1, as soon as two charts in X are compatible, corresponding charts in Tx will be compatible. And it's very easy to find the transition functions. And I would have said more about it. But I don't want to do it because it is a problem in my problem set, which certainly you will do. X may be orientable or not. This is its choice. But Tx is always orientable. Any idea why?
The first stiff Whitney class vanishes. The first stiff Whitney class vanishes.
What is vanishes?
The first stiff Whitney classes.
Thank you. Any other argument? It's very easy to write the matrix, Jacobian matrix, transition between two charts. As soon as you write it, you will see such a thing that the sign of the determinant will not present any problem. My friends, in the remaining 3 minutes, I want to say what I could say today, but I didn't. I will say this last time. Again, sometimes, unwillingly, we sort of step at algebraic terminology, what is worse, algebraic ideology. Manifolds have tangent vectors. Manifolds have manifolds Tx. Tx is a manifold of tangent vectors. What if we have a smooth map of one manifold X into another manifold Y? What happens to tangent vectors? What do you think? What do you think? Suppose we have a map of X into Y, very much smooth. But not more than that, just smooth map. What happens to tangent vectors?
You get an induced map on the tangent.
Induced map. What direction? Yes? Yes. Word who knows Sep-Dec classes certainly has no difficulty with that. The same direction. If you have a map of X into Y, then Tx is mapped into Ty. The corresponding map is called, you know this word, differential. The corresponding map is called the differential. Smooth maps have differentials. Smooth functions have differentials, and you sort of teach them in calculus classes. But actual differentials arise not only for smooth functions, but for smooth maps between manifolds. So smooth maps have differentials. This transition from a smooth map to a differential has all properties which you can imagine. Compositions correspond to compositions. Compositions correspond to compositions. The identity map, the differential of the identity map, believe me, is the identity map. By this reason, the differential of a diffeomorphism is an isomorphism. So many direct properties of differentials, which are extremely important, but all very trivial if you just want to check them. And this is what I will do next time.